Hello friends, this video on solutions part 27 is brought to you by examfear.com. No more fear from exam. Talk about the freezing point. Let's talk about the freezing point now. So what is freezing point? See, freezing point of a substance, at a freezing point actually what happens first, let me tell you. If it is at a freezing point, the solid phase will be in dynamic equilibrium with liquid phase. Let me write it here. Solid phase will be in dynamic equilibrium with liquid phase. This is my liquid phase. And let's suppose this is my solid phase. Both will be in dynamic equilibrium. Definition of the freezing point is it is a temperature. It is temperature at which vapor pressure of a substance in liquid phase is equal to vapor pressure of substance in solid phase. So if it has vapor pressure Vp1, if this has vapor pressure Vp2, right, the liquid phase and solid phase, so Vp1 is equal to Vp2. If that is the case, at a given temperature T, that temperature is called freezing point. Correct? So a solution will freeze when its vapor pressure will be equal to the vapor pressure of pure solid solvent. Hope you understand what I'm trying to say. So at a freezing point, what happens is the vapor pressure of the substance in liquid phase will be equal to vapor pressure of substance in solid phase. So the solution, if I have a solution which has solid and solvent, it will freeze when its vapor pressure will be equal to the vapor pressure of pure solid solvent, because this is my solid solvent, right? That is, I'm talking about the pure solid solvent. Let me write that statement actually. That is a critical statement. A solution will freeze when its vapor pressure is equal to vapor pressure of pure solid solvent. So with this concept, let's understand the depression in freezing point. So we have seen that a solution will freeze when its vapor pressure will equal to the vapor pressure of pure solvent, right? We have seen that. So as per Raoult law, when the non-volatile solute is added, for example in this case, its vapor pressure decrease. If it has vapor pressure P, it will become small p. Let this be P naught, this become P1, or this is P1 naught, this becomes P1, where P1 will be less than P1 naught, right? The vapor pressure will decrease when you add a solute to this solvent. Correct? So let me write that statement once again, right? A solution will freeze, and it will freeze when its vapor pressure, that is my P1, I'm talking about P1, will be equal to vapor pressure of pure solid solvent, and this is a constant value. This is a constant value for a given solvent. Example, water, it has a constant value. Now the only change is this guy. Correct? Now if you see here, to make a substance freeze, we have to decrease the pressure. Correct? Because this pressure is very low. This is very low pressure. Because we are talking about a solid solvent. Solids generally have very low pressure. So we decrease the pressure. Correct? So to decrease the pressure, we need to freeze it. But the moment you add a solute, the pressure already decreased. So for example, let's suppose this pressure was 100 Pascal. Now this became, let's suppose, 80 Pascal. And vapor pressure of pure, let's suppose, solid is, let's suppose, 10 Pascal. So in the first case 1, where I am having pure water or pure solvent, we need to convert this 100 Pascal to 10 Pascal. Correct. In case 2, when I am talking about this case, this is case 1, this is case 2. When I am talking about solution which has solute and solvent, I have to convert from 80p to 10p, because 10p is my fixed pure solvent, let's suppose, for pressure, right? So thus, if you see, the freezing point will decrease. Why? Because the pressure, I have told you, that is directly proportional to temperature. Here the difference is of what? 90 Pascal. Here difference is of 80 Pascal. So the pressure is directly proportional to temperature, so less temperature dip is required. Correct? Hope you understand. Since in this case it is from 100 Pascal to 10 Pascal, this case is 80 Pascal to 10 Pascal. So here only 80 Pascal difference is required, and pressure is directly proportional to temperature, so less temperature difference is required. So the freezing point will decrease. Correct? Now, so we have told that freezing point will decrease. Correct? So if my TF naught be the freezing point of pure solvent, because naught is for pure solvent, and let's suppose TF be the freezing point of solution, right? So the decrease is what? TF naught minus TF. The freezing point will decrease. If it is 10 degrees Celsius, it becomes 5 degrees Celsius. Now this is experimentally seen as, this is called depression in freezing point. This is called depression in freezing point. And experimentally it is seen that this is directly proportional to molality. Similar to elevation in boiling point, this is also directly proportional to molality, and to calculate this we need an equation. So the equation was, this is nothing but Kf into M. And what is this Km? Kf is nothing but my constant, and this constant is called freezing point depression constant. It is also called molar depression constant. It is also called cryoscopic constant. There are 3 names to this constant, right? And this again, this constant value, it depends on nature of solvent. So every solvent will have different Kf value. We'll see this, some of the Kf value of some of the common solvent in the next slide. And this unit will be same as my boiling point constant, that is nothing but kg per mole. If you want, you can derive this also similar fashion, right? Here if you want, I'll show you. Kf will become delta T by M. Let's write the unit. Delta T is in Kelvin. Moles is, molality is, this is molality, right? Moles per K. So the unit will be kg per. So let's see the Kf constant for some of the common thing. For water, the freezing point is 273 Kelvin. And if you see the Kf value, the unit is kg per mole, that is 1.86. Ethanol freezing point is 15.7 Kelvin and the Kf value is 1.99. Similarly, for other things, Kf value is given: acetic acid, diethyl ether, carbon disulfide, carbon tetrachloride, chloroform, benzene and cyclohexane. These are all experimental value of Kf. Let's take some application of freezing point pressure. There are various applications. The first, if you see, the seawater remain liquid even at temperature below 0 degrees Celsius. Have you thought why? See why? Because the seawater has sodium chloride dissolved and other minerals also dissolved. So with this, the freezing point goes down. So instead of 0 degrees Celsius, the freezing point may be -5 or -10 degrees Celsius. And thus, even at 0 degrees Celsius, the water is still in liquid phase. It is not in solid phase, and that helps actually. Correct? That is another good application of freezing point. If you wonder why at 0 degrees Celsius also the seawater is not solid, it is still liquid. The reason is because of the depression in freezing point, because of addition of these solutes, sodium chloride and other minerals. The next is the road salting. If you see the road salting, what is road salting? In the very, very cold countries, Russia, US, what happens is the roads are full of snow in winter season. Correct? To remove the snow, the best thing what they do is they put salt on the road. The moment you put salt on the road, what happens? The freezing point of ice will go down. Right? So let's suppose the temperature is 0 degrees Celsius. So at 0 degrees Celsius, if it is a pure water ice, it will become snow. But the moment you add salt to it, right, then the water will melt, the snow will melt. Why? Because now instead of 0 degrees Celsius, the freezing point may have become -10 degrees Celsius. Correct? But please note, the maximum we can lower is till -18 degrees Celsius. If the temperature is lower than -18 degrees Celsius, which is little rare, the salting won't help. But in most of the country, road salting helps, because the road salting will lower the freezing point of this snow, and with this the snow will melt even if the temperature is, let's suppose, 5 degrees Celsius here, 5 degrees Celsius. If it is pure water, if it is pure water snow or pure water ice, it won't melt, it will be hard. But the moment you put salt, what will happen is, sorry, if it is 0 degrees Celsius, it will be in the solid phase, but the moment you put salt, it will melt. And why it will melt? Because the freezing point will decrease. It's a very, very good application of depression and freezing point. Very, very useful in the cold countries. Also, the radiators which are used in the car in the cold countries, again, there we use ethylene glycol, and that is used as antifreeze. What happens is, if I use normal water in the radiator is used to cool down the engine. If I use normal water in the radiator, what happens is, in the cold country, when the temperature is, let's suppose, -10 degrees Celsius, the water in the radiator will become ice. It will freeze in winter. Right? It will freeze in winter. But we don't want it to freeze. If it freeze, you won't be able to start the car. So what happens is that water in this radiator is mixed with ethylene glycol. The moment you mix ethylene glycol in this water, the freezing point goes down. The freezing point becomes -30 to -40 degrees Celsius. Thus, even if the temperature is -20 degrees Celsius, let's suppose in the cold country, the radiator water will not freeze and the car will work perfectly fine. This is also very, very important application of depression and freezing point in cold countries. The last is, again, in the cold country, mostly the depression and freezing point is used in cold country. In fact, all the 4 applications which I told is helpful in the cold countries, not in the countries like India where it is not very cold. So if you see, some organisms, they live in extreme cold condition. For example, rainbow smelt. This is rainbow smelt. This is a fish, and it lives in a very cold condition, right? So thus, what they have done is they have evolved a means through which they produce high concentration of glycerol or some other compounds. So if this glycerol, what happens is this glycerol actually decrease the freezing point of water inside them, because they stay in -10 degrees Celsius, let's suppose. So the moment they stay in minus 10 degrees Celsius, the water inside them will freeze. They'll freeze and they'll die. But what they do is they produce glycerol inside them. This glycerol helps to decrease the freezing point. And thus, even if at the very cold condition, minus 10 degrees Celsius or minus 15 degrees Celsius, even if the water around them is freezing, they can comfortably live. They are generally Arctic living fish, at Arctic or Antarctic site where it's very, very cold. These are the various applications of depression of freezing point. So let's see how this Kf and Kv value is calculated. We won't use this formula as such, but let's understand the Kf value is calculated. I told you it depends on the nature of solvent. It is calculated using this formula, that is nothing but R into M1 into Tf square by 1000 delta H fusion. Here instead of delta H fusion I have delta H vaporization. See the value, R is the gas constant. It depends on the M1 is the molar mass of solvent. Again, it depends on the solvent. My Tf is the freezing point of pure solvent in Kelvin, and Tb is here the boiling point of the solvent in Kelvin, and delta H is my enthalpy of fusion of solvent, and delta VAP is nothing but enthalpy of vaporization of solvent. So using this formula, the KH and the KF and the KB value is calculated, but we won't use this formula as such in our class. Let's take some numerical now. 45 gram of ethylene glycol is mixed with 600 gram of water. We have to find the freezing point depression and the freezing point of the new solution. So we have, this is 45 gram of this ethylene glycol. Let's suppose this is glycol. This is added to, this is 600 gram of water. We have to find the freezing point depression. As I know, we already know that freezing point depression, the formula is delta Tf is nothing but Kf into molality of the solution. Correct? So Kf is something I can easily find from the chart. So Kf for water is nothing but 1.86 kg per mole. That is something we can get it from the chart. We can just see for water. So delta Tf we have to find, M we have to find, molality of solution. Molality of solution is nothing but moles of my solute, that is my glycol, by kg of solvent, that is water. So what is moles of glycol? Mass by molar mass. So what is the mass of glycol? 45. What is the molar mass of glycol? So molar mass of glycol I can find, carbon is 2, that is 2 into 12, plus hydrogen is 6, 6 into 1, oxygen is 2, 2 into 60, that is 32, 38 and 24, 62 gram per mole. So this becomes 62 gram per mole, and this is gram. Divide by kg of water. 600 gram of water is nothing but 600 by 1000 kg of water. Correct? You solve this, you get molality as 1.2 mole per kg. Now let's find delta Tf using this formula. So delta Tf is again Kf into M, the same formula I wrote. Nothing but Kf is my 1.86 K kilogram per mole into 1.2 mole per kg. This gets cancelled. What I am left with is 2.2 Kelvin. So the change in freezing point is 2.2 Kelvin. Correct? Now since this is water, the original freezing point is what? 273.15 Kelvin. So the new freezing point will be what? New Tf be nothing but 273.15 minus 2.2. Please note it is minus because the freezing point is going down, that is 270.95 Kelvin. So this will be my new freezing point of the solution. And we also found the depression in freezing point, that is 2.2 Kelvin. So both the values are derived. Again a pretty easy question. 1 gram of solute, the rate one let's suppose solute is 1 gram, is dissolved in 50 gram of benzene. That blue is benzene. This is 50 gram of benzene, right? This is benzene. Let me draw the figure only. This is benzene. Lower the freezing point by 0.4 K, that is delta TF is 0.4 K. The freezing point depression constant is given, Kf is Kf. You have to find the molar mass of solid. Pretty easy, delta TF is nothing but Kf into M. So and M is what? Molarity. So let's put the value here. So delta TF is what? 0.4 K. 0.4 K is nothing but Kf is 5.12 kg per mole into M is molarity, that is nothing but moles per kg, right? And mole is nothing but moles of moles of solute per kg of solvent, correct? So let me put this value once again, or 0.4 K and this K cancel, 0.40 by 512, right? This is kg per mole is equal to moles of solid is what? Mass of solid by molar mass. What is the mass of solid? 1 gram. So 1 gram by molar mass of solute divided by kg of solvent. 50 gram is nothing but 50 by 1000 kg. Please note it has to be in kg. Again the kg and kg will get cancelled. So when you solve this, the molar mass of solute you will get is what you get is 256 gram per mole. That is what you will get, because this one is in gram, 1 gram. So gram per mole is the unit that you will be getting. And that is my answer. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.